Hello friends. So, we discussed about the requirement of approximation in 2 dimensions, why those idealizations are used for 2 dimensional elasticity problems. They are very useful tools which can provide us very quick analysis, very easy to develop finite element mesh and easy to compute finite element results, and then visualize the results and take appropriate decisions for revision of designs. Now, we look at what are the requirements. We already saw the requirement that it has to be approximation in 2 dimensions, has to be in terms of displacements in x and y direction. So, u and v, and it has to be a interpolation C0 continuous element. So, now we look at the beyond these theoretical inferences, we get down to problem at hand, constructing the finite element as such. I mean particular finite element which can be used for 2 dimensional analysis. So, we look at what do we mean by finite elements in 2 dimension. So, as I said, it has to be a figure. I mean for a 2 dimensional domain is an area. So, the simplest geometry, 2 dimensional geometry which can enclose an area is a triangle, and a triangle is defined by 3 vertices. So, the moment I have these 3 vertices non coincident points, then those 3 vertices will enclose an area, and that I denote as omega e. So, element domain. Now, similarly, I can have 4 vertices defining a rectangle, right. So, again 4 vertices. So, this in area. Now, this rectangle can be of course, I can get the same area covered by using 2 triangles. If I consider this diagonal as one line, then this becomes this entire domain which is omega e, that can also be covered by using 2 triangular domains, while the number of nodes remain the same, right. So, there are various possibilities. So, the simplest 2 dimensional geometrical figures which meet the requirements that have been set forth, the C0 continuity requirements, they are these 3 noded triangle and 4 noded rectangle. Now, each node, the primary variable is defined as each node. So, u at these nodes are defined in they are numbered in counterclockwise order. So, I, j and k. So, these are the node numbers for the element particular element E, and for each node there are 2 degrees of freedom or 2 primary variables. So, u I v I, u j v j at node j and u k v k at node k. And similarly, for rectangle element it is I j k l, and 2 degrees or 2 primary variables or degrees of freedom at each node. So, u I v I, u the deformation along x direction, v the deformation along y direction, and u j v j at node j, u k v k at node k, and u l and v l at node l. So, nodal values of the primary variable, we do not know what these values are. What is done is we interior of the element, because this domain integral, that has to be the statement of residual is defined over this domain, individual domain, right. So, we need to find out what is the variation of these displacements, variation of u displacement with in x direction, variation of v displacement in y direction within this domain, element domain. So, triangular domain or this rectangular domain, how does this vary, how can we define polynomial variation, polynomial approximation of the displacement in within this domain. So, again we go by the same interpolation route, but now we need to look at two dimensional interpolation. So, finite elements are defined by the area enclosed in the region defined by the vertices. So, these are the we discussed triangle defined by 3 vertices, rectangle defined by 4 vertices, and vertices are essentially the intersection of two edges of the element. The variation of the primary variable within an element, within a finite element or within a subdomain E is defined by interpolation between the values of primary variables at a few fixed points, the vertices, and also some more points in between, which are which may be on the element edges, or and they can also be in the interior of the element, and these are called the nodes, right. So, nodes has a specific meaning with respect to interpolation theory, and we discussed the nodes and interpolation between the function values prescribed at the nodes in the or in our discussion, prior discussion on the interpolation theory. So, the function values or the primary variables, values of the primary variables which are as yet unknown, we do not know what the values are. So, u I v I, we just refer to them by these symbols u I v I, we do not know the numeric values for them. So, we treat them as unknown values, but we define the variation within the domain as an interpolation between these values at these fixed points, and that is achieved by interpolation model. So, u within the element E, so u hat approximation u hat within the element E as a function of x y is given as interpolation formula n I as a function of x y. So, this is the interpolation function or shape function for node I, ith node, multiplied by the value of the primary variable which is being interpolated. So, u at node I, and this summation, this term, I mean contribution from all the nodes of the element, they are added up. So, in triangular elements, this will be n I u I plus n j u j plus n k u k. So, that becomes the interpolation model. N I, n j and n k, they are functions of x and y. So, together the expression becomes a polynomial approximation for variation of displacement along x direction u in the interior of the element E as a function of x y. Similar approximation for v. So, n I v I. So, this interpolation functions remains the same. So, n I here for v is same as what we had here for u, right. There is no difference in this interpolation function, the function value changes. So, instead of longitude or displacement along x, we now look at the displacement along y at each node. So, v, the displacement along y as a function of x y is given as approximation is given as interpolation between the nodal values of displacement along y. So, v I, v j, v k. So, this summation, the upper limit n is the total number of nodes in an element. As I said, in a triangle, simplest triangular geometry that we saw, we had 3 nodes, and the simplest rectangular geometry we saw, we had 4 nodes. So, there can be, in case of triangular element, it can range from 1 to 3. In case of rectangular element, it can range from 1 to 4 for 4 noded rectangle. Of course, there are other higher order elements as well. We will see what it means by higher order. So, n I x y is the polynomial interpolation for node I. Now, what does it mean? N I as a function of x y is a polynomial interpolation for node I. As if you recall from our discussion in interpolation theory, the interpolation functions have to satisfy this condition that they have to evaluate to unity when they are evaluated at their own node. So, n I when it is evaluated at x I y I, x I y I being the coordinates of node I, n I should evaluate to unity at x I y I, but n I should vanish at other nodes. So, if n I is evaluated at x j y j, so j is another node. So, that should vanish. So, that is given by this interpolation condition. So, interpolation functions, they are also called shape functions. Some of the books they are referred to as shape functions, because they define the shape of the approximation, the variation of the primary variable within the element domain. So, interpolation of shape functions are defined such that n I evaluated at x j y j, I and j they are the nodes of the element, is equal to delta I j. Delta I j is a Kronecker delta. So, that is equal to 1 only when I is equal to j, and if I is not equal to j, it is 0, right. So, that means for a triangular element, n I should be unity at node I, and it should go to 0 at node j, and it should go to 0 at node k. So, I can define this variation. So, if I have this so this is I, j and k. So, I can draw this variation. So, this is how n I will look like. N I as a function of x y. So, this is unity at node I, it goes to 0 at node j, and it goes to 0 at node k, and this is linear variation. And when you see this at this edge j k, it is equal to 0, n I is uniformly equal to 0, because this value is 0 here, this value is 0 here, and this a linear variation 2 points. So, there is only one variation, and that is only 0. Similarly, for the jth node, interpolation function or shape function might look like this. So, this is so n j, and similarly for n k, it will be unity at n kth node, and it will vanish at linearly at I and jth node, right. So, this is the variation. This is how interpolation functions, these interpolation functions are they vary over the domain, and together they will have this approximation constructed for the finite element model. So, the polynomial approximation for primary variables within an element can be arranged now in a matrix form. So, as I said, n 1 u 1 plus n 2 u 2 plus n 3 u 3 plus n n u n up to n n u n, right. And similarly for component v, displacement v, so it will be n 1 v 1 plus n 2 v 2 plus all those terms, and then finally n n v n. So, we accumulate contributions from each node. So, together collectively we refer to them as u, the variable for the element variable collection variation of primary variable within the element is defined as matrix of interpolation functions for all the nodes and multiplied by the nodal values of the primary variables. So, u 1 v 1, u 2 v 2, u 3 v 3, U4, V4, etc. Right. So, this is fine, the condition is defined. Now, we can see that for the triangular element, as we saw, n I at x I y I is equal to 1, n I at x j y j is equal to 0, and n I at x k and y k is equal to 0. These are the three conditions. Similarly, for n I, similarly for n j, I can write three conditions. So, at ith node it is 0, n j at x j y j is equal to 1, and n j at x k y k is equal to 0, right. And similarly, for n k, the interpolation function for node k, so it should vanish at x I and y I, it should vanish at x j and y j, and it should evaluate to unity at x k y k. So, for each of these functions, these three functions are they are independent of each other, that we are only looking at what is the behavior of n I at node I, what is the behavior of n I at node j, and what is the behavior of n I at node k, right. So, ostensibly there is no dependence of n I on n j and n k, right. We are not invoking anything from n j while defining the requirements of n I and so on, but they are in fact related to each other. We will see why, or not related to each other, they have to satisfy one more condition, which apparently automatically gets satisfied in this case, but we may not be always so lucky. But let us keep things at the moment simpler at the moment. So, this there are three conditions for n I. So, that means there are I have three constraints to define n I, and n I has to be a first degree polynomial, because the variation n I defines the variation of displacement u and v, n I, n j, n k together, these three in for 3 dimensional triangular element, right. So, u is equal to n I u I plus n j u j plus n k. Let me be explicit about x y dependence of n u k, right. So, n I, it is also dependent on x and y, n j is a function of x and y, and n k, u I, u j, u k, they are values of the primary variable at nodes I, j and k. So, the variation that we have comes from these interpolation functions, and this variation u we know from our boundary term in the weak form of the method of weighted residual, that this has to have at least first order derivative non vanishing. First order derivative should exist, right, and first order derivative should exist, that means I need to have first degree polynomial terms in this expression. So, what are the first degree polynomial terms in 2 dimension? X and y, these are the linear terms, and I also need to have one constant term, right. So, I can define this n I because I have 3 constraints to evaluate, I can evaluate 3 coefficients. Any function polynomial approximation, I have 3 constraints. So, I can only evaluate 3 coefficients for this function. So, I define n I as alpha I plus beta I x plus gamma I y, right. So, this is the polynomial, first degree polynomial, which alpha, beta and gamma for node I can be evaluated by these 3 constraints. I just substitute the values for these 3 coordinates x I, y I, x j, y j and x k, y k, and evaluate these to be according to this condition. For example, I can say that 1 0 0 1 x I, y I, x j, y k, sorry, x k, y k, alpha I, beta I, gamma I, right. So, now alpha I, beta I, gamma I can be evaluated by simply inverting this coefficient matrix x I, y I, x j, y j, x k, y k, and this will be invertible because the 3 nodes are far away, are distant, right. So, none of the rows and columns are linearly dependent. So, this matrix itself is invertible. So, alpha I, beta I and gamma I can be evaluated by inverting this matrix and then multiplying that inverse with 1 0 0, and then we can substitute this alpha I, beta I, gamma I, and that is what will fetch us the interpolation function for node I, and similar expressions can be, similar kind of equations can be set for n j and n k as well. So, 0 1 0 will be equal to 1 x I, y I, 1 x j, y j, 1 x k, y k, alpha j, beta j, gamma j, and so on. And that is the way we can work out these interpolation functions. So, unknown variations, we will spend more time on this development of finite element and the interpolation function, because as I said earlier, everything else in finite element method is pretty automatic. It is only in the definition of the interpolation, the development of the elements, that the differences arise, and we will spend some time on discussion of construction of finite elements and the interpolation functions, how to derive interpolation function and what properties interpolation functions should satisfy. So, the unknown variation of the displacement field within the element subdomain can be represented by a few discrete nodal values of the displacements if appropriate interpolation functions are specified, and that is what we discussed, how these appropriate interpolation functions are derived by imposing a limiting behavior on them. And a complete description of a finite element is provided by its node and corresponding interpolation function. So, if it is a 3 dimensional triangular element, 3 node triangular element, if I know where the nodes are located, the coordinates of the nodes, and if I define the interpolation function for those nodes, that is the complete description of the finite element, triangular finite element that I need, right. I do not need anything else for formulating the problem in terms of that particular element. The nature of approximation depends on the degree of interpolation polynomial, which in turn depends on the number of nodes for interpolation. So, because the number of nodes that I choose, they define the number of constraints that I have, and those constraints define the number of coefficients, independent coefficients that I can evaluate by satisfying those constraints. So, that the number of independent coefficients that I can evaluate, they put a restriction on the degree of polynomial terms that I can use. So, if I need to use higher order degree polynomials, let us say second degree polynomial, I need to add more nodes in the approximation. 3 nodes will not be sufficient to approximate to construct a second degree polynomial approximation in triangular domain. So, the basic requirements of polynomial approximation for the convergence of finite element solution, I repeat, I have discussed this earlier, the capability to represent rigid body motion and the capability to represent constant strain states, and these are the restrictions that we adhere to while constructing the interpolation functions, and we will discuss more on this in our next lecture. Thank you.